Continue lecture. Group 13 element does not show the irregular trend in the element of the groups in the melting and the boiling points. Melting and the boiling point depends on the crystal structure shown by the boron or galliums. All in the aluminum, indium, thulium have the close packed metallic structure, therefore their melting point decreases from aluminum to indium and increases for the thulium. Boiling point of boron is high, but it decreases from aluminum to thulium. Deficient compounds. Lewis acid character showing the electron deficient compounds are comparator in which the number of valence electrons available are less than the minimum electron required from the covalent bonds. Diboron molecules. Diboron molecules. Molecular formula is B2H6, 2 boron atoms and 6 hydrogen atoms. B2S6 is the diboron molecule. In the B2S6, electron deficient molecule can also be defined as the molecule which contain atoms. Electron deficient molecule can also be defined as the molecule which contain atoms that have more stable low energy atomic orbitals than the total number of electrons in the valence shell, example diboron molecule. So if you see the boron molecules, then the boron having the 3 valence electron in the outermost shell, that 3 electrons are involved in the bondings, and here the bondings are of special types. We looks at the borons having the 4 bonds, but actually borons having the 3 bonds, one extra, that is the special types of the bonds. If you see here, it is actually representation of the diboron molecules. In the case B2S6, that is boron having the 2 hydrogen atoms. Here is also boron having the 2 hydrogen atoms, clearly mentioning the covalent bonds. So these 2 bonds do not have the problems. It is a clear. We know that this is a covalent bond by the sharing of the boron and the hydrogen atoms. But some doubts and some new things arise from this bridge, looking bridge like hydrogen atoms inside hydrogen atoms. So that form the 2 bonds. Hydrogen form the 2, actually hydrogen having the tendency to form the 1 bonds. Without hydrogen is the monovalent atoms, but here is one clear covalent bonds and another is the dash bonds. Here is also clear covalent bond boron hydrogen and another is the dash bond. So in the diboron molecule, each hydrogen atom has 1 atomic orbital, 1s. In case of the boron atom, there are totally 8 atomic orbitals. In the diboron molecule, each hydrogen atom has the 1 atomic orbital, 1s. In case of the boron atoms, there are totally 8 atomic orbitals. In the diboron molecule, each hydrogen atom has the 1 atomic orbital, 1s. In case of the boron atom, there are totally 8 atomic orbitals. Therefore, in diboron molecules, Total number of lower energy orbitals are of 14, but total number of valence electrons are only 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Only 12. 14s, but total number of valence electrons are only 12. As the number of valence electrons are less than the number of low energy orbitals in this molecule, hence it is the electron deficient molecules. Hence it is the electron deficient molecules. So total number of valence electrons are the 12. Total number of low energy atomic orbitals are the 14s. So it is less than the 14s, that is 12, means it is the these types of molecules are called as the electron deficient molecules. Diboron as a Lewis acid. We know that we have seen the Lewis acid, that is AlCl3, aluminum trichloride, well known. We use this AlCl3 for the for the Friedel-Crafts reactions. So in case of the Friedel-Crafts reaction, whenever we use the AlCl3 as a Lewis acid, that Lewis acid is useful for accepting the lone pair of electrons, and after accepting the lone pair of electrons, it facilitates the breaking of that particular atoms to which it form the bonds. Means that especially for AlCl3 is used for the formation of new bond, so that the old bond can be easily break, means for the facilitation of the breaking of the bonds. So these types of atoms which accept the lone pair of electrons, it is the Lewis acids, and it accepts the lone pair of electron only when if it is having the electron deficient atoms. It means that if it is having the electron deficient atoms, so it will in the condition to accept the lone pair of electron so that it can complete its octet. So electron deficient molecules can do these things. And diborons, obviously we saw the diborons having the total 14, and having the lone pair of electrons 12, valence electrons is 12, but total number of lower energy orbitals are the 14s. It is the electron deficient, so diboron comes under the category of the Lewis acid. So the Lewis acid is defined as the substance which can accept the electron pair from other substance, which can donate the electron pair and form the coordinate covalent bonds. Acid is the electron pair acceptor and base is the electron pair donor. So in case of the B2S6 molecule, symmetry is observed. In symmetrical cleavage of the B2S6, which is broken into the 2 BS3, and each of which form the complex with the Lewis base, that is the NCS3 by 3 BH4. The reaction of B2S6 with ammonia NH3 NH3 form the two molecules. One is the BH4 minus, another is the BH2 NH3 by 2 plus. So it shows that the boron is the electron deficient and accept the lone pair of electrons. Next is the example of electron deficient molecules. There are number of examples of boron, that is B2S6 is electron deficient, BF3 boron trifluoride is the electron deficient, BCl3 is electron deficient, AlCl3 is the electron deficient. Halides of the borons. Boron combines with the halogen X to form the trihalides. 2 boron plus X3 gives the 2BX3, 2BX3, where X is the chlorine, bromine, iodine. Boron trihalide are covalent in nature and exist as the monomeric molecules. 2B6 gives the 2BX3, where X is the chlorine, bromine, iodine. Boron trihalide are the covalent in nature and exist as the monomeric molecules. In the boron trihalide BX3, boron is the sp2 hybridized state and 3BH bond are formed by the axial overlap of sp2 hybridized orbital of the boron and p orbital of hydrogen. So boron is the 1s2, 2s2, 2p1. In the ground state, electronic configuration of the boron is the valence shell 1 2s electron 1 p electron, but when excited that s electrons become unpaired and went on the p orbitals, so that we will get s1 p2, it is sp2 hybridized atom. 3 unpaired electrons of boron atom react with 3 halogen atoms. 3 unpaired electron of boron atom react with 3 halogen atoms and forms the 3 covalent bonds. 3 unpaired electron of boron atom react with 3 halogen atoms and forms the 3 covalent bond, that is the BX3. Electron donor atom like NH3 F- amine, it is forms the adduct, that is the NH3 react with the borons, means the nitrogen atoms, giving the lone pair of electron to boron. Boron accept that lone pair, complete pair of electron, that is coordinate covalent bond and form the adduct. In the boron trihalides, electron density of boron atoms from Bf3 to the Bi3 decreases. So Lewis acid character in case of the boron Bf3 trifluoride increases as the follow. That is Bf3 less than the BCl3 less than the Br3 less than the Bi3. This order is reversed in case of the Lewis base. Hydrides of the borons. Hydrides of the boron are sometimes called as boranes. It can be classified into 2 series. One is the BnHn plus 4 called as the nidoboranes. BnHn plus 6 called as the arachoboranes. Simplest hydride of the boron is the diboranes B2S6. It is prepared industrially scale as the 2BF3 gaseous plus 6Li(H) solid. On the arrow 450 kelvins gives the 2B2S6 gaseous plus 6LiF. In laboratory it can be prepared as the 2NaBH4 plus I2 gives B2S6 plus 2NaI plus S2. Hydrides are the covalent compounds and are also called as the boranes by analogy with alkanes. Boranes have been grouped into 2 classes. Structure of diboranes B2S6. Electron diffraction data suggests that following bridge structure for the diboranes is the having the angles 120, 97s and bond length are the 0.13 nanometers. Bond length 0 to 13 nanometers structure of the diboranes. From the figure, there are 4 terminal hydrogen atoms attached to the 2 boron atom, which coplanar. Remaining two hydrogen atoms are involved in the formation of boron hydrogen boron bond or bridge in case of the boron hydride boron, hence the hydrogen atoms called as bridge hydrogen atoms. These two hydrogen atoms lie perpendicular to the plane of the molecules and they prevent the rotation between the boron atoms. Structure is satisfied by the methylations. Hydrogen atoms are successively replaced by CS3 groups, forming the B2S6 CS3 by 4 further methylation. It breaks into the BCS3. This clearly explains that the 4 hydrogen atoms attached to boron atoms are same type, whereas remaining 2 hydrogen atoms on replacing the molecule get rupture. So this is all about the bondings in the boron atoms. The remaining part we will discuss in the next lecture. Thank you very much.